Look at two horizontal lines, one seemingly longer than the other, but measure them, and you'll find they're exactly the same length. This is the famous Ponzo illusion, and your brain just fell for it. Don't feel bad though. This mistake reveals something fascinating about how your mind works. Your brain just made a prediction based on countless prior experiences with perspective and depth. It looked at those converging lines and automatically calculated that the upper line must be further away. And if two lines appear the same size but one is further away, the distant one must be larger, right? That's the probability calculation your brain just ran without you even knowing it. Every single moment of your conscious experience, what you see, hear, feel, and even think, may actually be a sophisticated probability calculation performed by your brain. Recent research suggests that a significant portion of perceptual illusions can be explained through these kinds of prediction errors, where your brain's strong prior beliefs override the actual sensory evidence. Think about that for a moment. Right now, as you watch this video, your brain is running countless probability calculations, making predictions about everything from the next word I'll say to whether that movement in your peripheral vision is a threat. And it's doing all of this in a fraction of a second. Research shows the delay between sensory input and conscious perception can be as short as 13 milliseconds for visual cues, though full conscious processing typically takes between 75 to 150 milliseconds. What if your brain isn't just responding to the world, but is actually constantly predicting it? What if every experience you have is really your brain's best guess about reality based on prior knowledge and current evidence? This is the fascinating premise of the Bayesian brain hypothesis, and it might just change how you think about thinking itself. Consider this. When you hear someone speaking in a noisy room, how do you understand them despite missing half the words? When you catch a ball, how do you know where it will land before it gets there? When you recognize a friend's face in a crowd, how do you do it instantly, even from an angle you've never seen before? These aren't just reactions, they're predictions. And understanding how your brain makes these predictions could unlock some of the deepest mysteries of consciousness itself. Let's shatter a common misconception. Your senses don't work like a camera or microphone, passively recording the world. Instead, they're more like a scientist, constantly making and testing hypotheses about reality. This insight is revolutionizing our understanding of how perception actually works. Try this fascinating experiment. Watch a video of someone saying "ba" while the audio plays "f-ah." What do you hear? Remarkably, many people will hear "via," a sound that wasn't actually present in either the video or audio. This is the McGurk effect, and it demonstrates something profound about how your brain processes information. The effect varies significantly across cultures and languages. For instance, native Japanese speakers experience a weaker McGurk effect compared to native English speakers, even when unisensory accuracy is equivalent between the two groups. But why does this happen? The answer lies in how your brain uses Bayesian inference, a mathematical framework for combining prior beliefs with new evidence. Think of it like this. Your brain has prior beliefs about how lips moving in certain ways connect to specific sounds. When it receives conflicting visual and auditory information, it doesn't just pick one or the other. It calculates the most probable explanation given all available evidence. This Bayesian process isn't just about optical illusions or speech perception. It's happening constantly in every aspect of your sensory experience. When you're at a noisy party, how can you still understand what your friend is saying despite the cacophony around you? Your brain is using prior knowledge about language patterns, context, and your friend's speaking style to fill in the gaps in the acoustic signal. It's making predictions about what words are most likely given the partial information it receives. The timing of this process is remarkable. Research shows that prior knowledge influences conscious perception as early as 80 to 95 milliseconds after a stimulus appears. That's faster than you can blink. Your brain is literally predicting what it expects to see and hear before you're even consciously aware of it. This predictive processing becomes even more fascinating when we look at experts versus novices. Research on athletes shows that experts have significantly faster reaction times in their domain of expertise, not because their basic reflexes are faster, but because their brains have better predictive models. Their extensive experience allows them to anticipate events more accurately, leading to what appears to be superhuman reaction times. Consider what happens when these predictions go wrong. In chronic stress conditions, the brain's Bayesian updating mechanisms can become impaired. Studies show that chronic stress leads to atrophy in key brain regions, like the hippocampus and prefrontal cortex, which are essential for updating our predictive models based on new information. This can lead to rigid thinking patterns and difficulty adapting to new situations, a stark reminder of how crucial these predictive mechanisms are for normal cognitive function. Watch a baby play peekaboo, and you're witnessing one of the most sophisticated learning engines on the planet in action. That giggling infant isn't just being entertained. They're conducting complex experiments about object permanence, causality, and the nature of reality itself. And they're doing it with an efficiency that puts our most advanced artificial intelligence systems to shame. Consider this remarkable fact. While our most sophisticated AI systems struggle with basic object permanence tasks, human infants master this concept within their first year of life. Recent research comparing infant learning with AI systems is particularly revealing. The latest AI model for object permanence, called loci looped, achieves impressive results with a mean tracking error of 2.7, significantly better than previous models. Yet even this advanced system can't match the intuitive understanding that babies develop naturally. What makes infant learning so remarkable is its Bayesian nature. Babies don't just passively absorb information, they actively test hypotheses about their world. Every time an object disappears behind a screen and reappears, they're updating their probabilistic model of how objects behave. Consider what happens when a baby drops a spoon from their high chair. The first time, it might be an accident. The second time, they're testing what will happen. By the third time, they're conducting a controlled experiment, varying the force, angle, or starting position to see how these factors affect the outcome. They're literally building a probabilistic model of gravity, physics, and cause and effect relationships. The implications of this are profound. Traditional learning models often assume that knowledge is built up gradually through simple association and reinforcement. But the Bayesian framework suggests something far more sophisticated is happening. Babies are performing complex statistical inference, weighing evidence against prior beliefs, and rapidly updating their mental models of the world. Research on psychiatric conditions suggests that many symptoms can be linked to specific types of prediction errors. For instance, studies have found that reduced prediction error signals in specific brain regions correlate with increased severity of certain symptoms. In depression, reduced prediction errors in the striatum and midbrain correlate with increased anhedonia. In schizophrenia, blunted prediction error signals in regions like the caudate and thalamus correlate with increased psychotic symptoms. Understanding this Bayesian learning engine isn't just academically interesting. It has profound implications for education, artificial intelligence, and mental health treatment. By understanding how infants learn so efficiently, we might be able to design better learning algorithms, create more effective educational approaches, and develop new treatments for conditions involving disrupted prediction mechanisms. The next time you see a baby playing with toys, remember, you're watching a remarkable prediction machine in action, one that puts our best AI systems to shame. That drooling, giggling infant is running complex Bayesian calculations, building sophisticated mental models, and conducting clever experiments, all while making it look like simple play. You're standing at a crosswalk, about to step off the curb. In the split second before you move, your brain performs a remarkable feat of probabilistic engineering that would make the most sophisticated computer algorithms jealous. Your brain isn't simply checking if there are cars coming. It's running a complex Bayesian calculation, weighing multiple streams of evidence against prior experiences. The sound of approaching engines, the time of day, the speed of visible vehicles, the behavior of other pedestrians, all of this information is being integrated with your lifetime of street crossing experience to calculate the probability of a safe crossing. Consider professional athletes, where the stakes are high and decisions must be made in milliseconds. Studies have revealed that elite athletes don't just have faster reflexes, they have more sophisticated predictive models. Research shows that expert athletes in sports like soccer and volleyball can better predict and react to cues, leading to significantly shorter reaction times. For instance, experienced goalkeepers demonstrate remarkably faster reaction times on domain-specific tasks compared to novices. But here's what's fascinating. This same Bayesian decision-making architecture applies to every aspect of your life, from casual social interactions to navigating a grocery store. When you're having a conversation, your brain is constantly predicting what the other person will say next, calculating the probability of different responses based on their facial expressions, tone of voice, and your prior knowledge of their personality and beliefs. The speed of this process is remarkable. Research indicates that the brain can make initial predictions about sensory input in as little as 13 milliseconds, though full conscious processing typically takes between 75 to 150 milliseconds. These predictions happen faster than you can consciously perceive them, yet they shape every decision you make. Studies show that chronic stress can significantly impair these Bayesian updating mechanisms. When neurons in the hippocampus and prefrontal cortex, key regions for decision-making, undergo stress-induced atrophy, our ability to update our predictive models based on new information becomes compromised. In clinical settings, for example, research has shown that many psychiatric symptoms can be linked to specific types of prediction errors. Depression and schizophrenia both show distinct patterns of disrupted prediction error signaling, with the severity of symptoms correlating with the degree of disruption in specific brain regions. The next time you make a seemingly simple decision, whether it's crossing a street, catching a ball, or choosing what to say next in a conversation, remember that you're witnessing your brain's remarkable predictive architecture in action. Every decision, no matter how small, is the product of sophisticated Bayesian calculations happening beneath the surface of consciousness, shaped by a lifetime of experience and learning. What happens when our brain's prediction machinery goes awry? The answer reveals not just why we make mistakes, but also provides fascinating insights into consciousness, mental health, and the nature of reality itself. Consider the base rate fallacy, one of the most pervasive cognitive biases. Research shows that people routinely overestimate the probability of having a disease given a positive test result, often by 10 to 20 times the actual probability. From a Bayesian perspective, this isn't just a simple error, it's a fundamental failure to properly weigh prior probabilities against new evidence. We focus intensely on the new information, the positive test, while neglecting the critical background rate of the disease in the population. Studies on the conservatism bias show that people typically update their beliefs about 50% less than they should after receiving new evidence. Our brains are running Bayesian calculations, but they're weighing prior beliefs too heavily against new information. Research has found that many psychiatric symptoms can be linked to specific types of prediction errors. In depression, reduced prediction error signals in the striatum and midbrain correlate with increased anhedonia, the reduced ability to feel pleasure. Research shows that precision weighting in sensory processing, our brain's ability to accurately discriminate and integrate sensory information, changes significantly as we age. Older adults experience declines in auditory temporal perception, starting around age 20, along with changes in visual temporal perception and multisensory integration. Studies have found striking differences in how people from different cultures process sensory information. For instance, people from Western cultures, which value individualism, tend to focus more on individual objects, exhibiting analytic perception. In contrast, people from East Asian cultures, which value collectivism, are more likely to pay attention to context and relationships between objects, showing holistic perception. Research on bilingual individuals shows that prediction patterns differ between first and second languages. Studies indicate that second language processing often shows a later onset of prediction compared to first language processing, suggesting that the strength and accuracy of our predictive models depend heavily on the frequency and depth of our language exposure. Research shows that there's a measurable delay between sensory input and conscious perception, typically between 100 to 500 milliseconds, depending on the type of stimulus. During this brief window, our brains are running complex predictive calculations that will determine what we consciously experience. In other words, what we think of as reality might actually be our brain's best prediction about what's happening, rather than direct perception of the world. The idea that your brain is a prediction machine, constantly calculating probabilities and updating beliefs, has profound implications for how we understand consciousness, learning, and mental health. But rather than simply accepting these ideas, let's engage with them critically. First, think about language learning. If your brain is truly a Bayesian prediction machine, how would this change your approach to learning a new language? Consider that bilingual studies show prediction patterns differ significantly between first and second languages, with second language processing often showing delayed prediction onset. Second, reflect on your own experience with prediction errors. When was the last time your brain's predictions led you astray? Perhaps it was a social situation where you misread someone's intentions, or a physical task where your timing was off. Remember that studies show we update our beliefs about 50% less than we should when confronted with new evidence. How might this affect your daily decision-making? Third, consider the implications for artificial intelligence. Current Bayesian brain-inspired algorithms show promising results, with some predictive coding networks demonstrating performance improvements of up to 4.45% in challenging tasks. Yet babies still outperform our most sophisticated AI systems in basic tasks like object permanence. What might this tell us about the future of AI development? Finally, contemplate the implications for mental health treatment. Research has shown that many psychiatric symptoms correlate with specific types of prediction errors in the brain. How might understanding these mechanisms lead to more effective treatments? These questions aren't just academic exercises. They touch on fundamental aspects of how we learn, think, and perceive the world around us. By understanding our brain's predictive nature, we might not just explain how we think, but revolutionize how we approach education, artificial intelligence, and mental health treatment.